We're going to look at how the Tock components interact with each other to make an embedded system, and this will lead up to the demo with the virtual LEDs. In that, we'll also examine the policies, security, and trust levels that are common to be able to make the Tock system safe. So the star of the show is the kernel, and the kernel manages resources, it maintains system stability, it does this in part with how it schedules the applications, which there's multiple ways to do that, the default being a round-robin schedule. The kernel also, besides talking to the applications, needs to talk to the hardware, and it does this with the interface with the hardware drivers through the hardware interface layer. And these traits in Rust are designed to be non-blocking and asynchronous. The reason why is because a lot of the hardware tasks of what the kernel is going to want to reach out and do are I/O constrained, and so it's going to be waiting around a lot, which is why the asynchronous model is used. On the other end of the kernel is it's talking with capsules, and these capsules are what interacts with user space processes and then also with the hardware through the drivers. So the capsules they can allow the users space processes to access, let's say, turn on an LED, or to be able to drive a digital to analog converter. And this is done through a single event loop, so the capsules are running in the kernel with that event loop. And then finally, the user space processes, the whole reason Tock exists, is to look at how they interact with the kernel and the capsules through API calls, and then also how their isolated memory space is used by the capsules and how that provides safety and security. So talked about capsules a bit, and we can look at those on the next slide. User processes interact at the kernel level normally with capsules. The reason why is because capsules have what the user processes need to get things done, such as serial communication, UART, or I2C, also hardware features on the embedded board, things like LEDs or buttons. And there's also other hardware features that a user process may need, has access to accurate hardware timers to be able to be alerted at specific times, and that can be through alarms. Now, the way the user processes interact with the capsules in that kernel level code is through the kernel syscalls. So these are APIs that are defined that the user processes can use to reach down to the capsules to make requests. One of the questions, though, is if Tock doesn't have a heap allocation, how, when you run and you can add and remove different user processes, how can you manage memory for some of these different hardware or serial interactions? So for example, with the UART, often you'll need a buffer for serial communications to be able to store data that's to be transmitted or to store data that the device is receiving before the process can handle it. Tock has a clever way of dealing with that, and that is that the memory used by the capsule is granted from the process space, where the process can then have have the best sense of how much memory it's going to need. And that way, as you get multiple processes running too, they can each grant their own memory to the capsules to be able to use for their buffering or for other, let's say, like information that needs to be transferred where there's more information than you would want to pass through a syscall. So all of these, and we'll get into more details of how this actually works, but the main idea is that the capsule memory for these buffers and for things being used within the process is granted by the process. That way, if the process shuts down, all of this memory is also freed. So these capsules don't just interact with the user processes, but they can also interact with other capsules. So they can provide services like a virtual UART that the specific UART capsule that's interacting with the user process needs, or those alarms that are used by the LEDs or buttons, and those can also be used by the user application process. So it's a very modular system, and these like broader applications for the capsules would be things like inertial navigation, environment sensors, those kind of things. So we've talked about how the capsules interact with the processes and give an example to help illustrate that. When a process wants a capsule to perform an operation, it interacts with that capsule through the syscall command. The way this works is that the process uses that syscall API and it issues a command. That command triggers a hardware exception trap that the kernel intercepts, and it then calls the do process function, which acts like a router. That it takes that command, which includes the operation, the process wants the capsule to perform and which capsule it's referring to. And so it uses that information in the command to route to the specific capsule. And that's done with the handle syscall function. And once that occurs, when the capsule is done with that command, it then returns back a return value with the set syscall return. It's important this loop is important because this is a synchronous call. So a lot of the calls are asynchronous, and that the process can set it. It'll get a call back later when it's done. But for the command, it's synchronous. So when the process issues the command, it sits there and waits until it gets back this syscall return value. Therefore, it's important that this loop happens quickly so that there's not a lot of blocking or stalling of the application. And then this can then be used to set flags or trigger events that are going to be longer running or set things up for longer running. We can, from here, pointed out a couple of the functions, but we'll take a little bit of a look at the code to get a sense of how this is implemented in Rust. So the do process function calls the handle syscall, which is shown here, and that includes the user process that made the call and also the syscall itself that it used. And that syscall has a driver number. And so that driver number is used with the with driver to be able to determine what the driver is. So there's a match statement here. And based on the capsule that that driver number refers to, it's going to return a function of that then the syscall driver lookup that this can then use for making the actual call with the command information. The policies in security can be grouped into three broad trust levels, and that is the most trusted, which is the kernel and hardware abstraction layer. And here, unsafe is allowed, and if any of the code crashes, it can take down the whole embedded system. So it's assumed that the code is fully trusted, and that's one of the reasons that all of the kernel code is in the Tock repository. So it's available, it's auditable, and there's not this downstream risk of another dependency causing problems in the most trusted region. A step down from trusted is privileged, and that's where the capsules lie. So the capsules not allowed to have unsafe code, but they're considered in the untrusted region that the security is provided by the language sandbox, so by not allowing unsafe instead of hardware memory protection. The advantage here is that you get zero cost safety because it's done at compile time. Now, with the capsule code, there is the risk if the capsules hang, if they're not cooperative in that kernel event loop, they can hang the system. So it is important to make sure that the capsules won't hang the kernel. Outside of all this is the completely untrusted, unprivileged user space processes up here. So in here would be not only the applications that are running on the embedded system, but services they may need, such as the Thread wireless protocol service and other services would be available here. And all of these, if they crash, they won't take down the entire system. Here, one of the reasons they are completely untrusted is because unsafe is allowed, since you can have whatever programming language you want running here and accessing memory. That's also why for this part above the kernel that it's important that the processor has a hardware memory manager to be able to manage the memory on there. So this is the broad categories of how the policies and security are implemented through Rust traits and through safe and unsafe code. The previous slides can be summarized in a few bullets. First, the Tock components are important because they support running isolated applications while allowing access to system resources in a safe way. And those components, the kernel, capsules, and user processes, they work together in a single-threaded event loop. Specifically, the capsules interface between the hardware and user processes, and they really rely on Rust type system for the isolation and safety during the compile time. And the way those user processes communicate with the capsules and kernel is through the syscalls, which form the communication bridge between the user processes and the hardware resources. As we saw previously, that the safety and security are built on layers of trust, where at the most trusted level are the kernel and hardware abstraction layer, and then from there the capsules, which are privileged but still sandboxed by Rust through those compiler traits. And then finally, the user processes, which are the least trusted and isolated by the hardware memory manager. What's also great about the Tock operating system is that there's extensive documentation and tutorials to support the hands-on development. What can be difficult with embedded systems, learning embedded systems, is getting a hold of the hardware. And Tock has quite a few tutorials to get your feet wet without having to have any embedded hardware. And that's what we'll look at next. So what we're going to look at is the Tock system in action with, of course, lights blinking. But these are going to be virtual lights. And this is going to demonstrate both the kernel and user application. What's great about this is no embedded hardware is needed. You can be able to set it up in a virtual environment. QEMU is used. It could be run on Windows, Mac, or Linux. And the blinks for this will be it's going to have a simulated LED counting pattern. But what's neat about this is that the code that's running could easily then be moved over onto an embedded board and it would do the same thing. So, so we're going to then look at the user process Rust code and the kernel command line interface, and then here are the resources for the demo that we'll look at with the Tock book for setting it up, and then the specific examples and that blink example.